Okay, so today I just wanted to do a little hands-on on maximum likelihood estimation, and we'll move on from there to again a hands-on kind of a example of expectation maximization, and hopefully at the end of this you'll if you're not comfortable with the idea of either, you'd be kind of get a more intuitive understanding of what we're doing. So we'll start with some very simple data. This is kind of some discrete observations, and we know this comes from a Poisson distribution. So for example, let's say you're observing an event, maybe people passing in front of a store, or in a given hour, or maybe number of mutations per let's say 1,000 kilobases. So your first observation is 3 events happening, then 0 events, then 1 event, then 2 events, 1 event, etc. Now the idea is in maximum likelihood estimation, we want to estimate something about this random variable. And this is a random variable. These are just the samples from a random variable. Each hour, the 12th hour, the sampled value was 0. If you sample it some other time, it might be 6. If you sample it another time, it might be 3. But if you notice, we never see something like 72, or you don't see an inordinate number of zeros. So this kind of gives us a general idea about what to expect from this random variable. Namely, we can estimate its average rate. And obviously we do that very simply with the Poisson distribution. You can just take the average of all of your observations, and that is, like we saw in class, the maximum likelihood estimation of the mean. So what I'll do is I'll just copy this data into a normal spreadsheet. You can use Excel. I'm going to use Google Sheets in case some of you don't have Excel installed. Google Sheets is always available. So let's give this a name, EM, let's say MLE EM. So these are our, I'm going to put a few lines at the top. So this is our data, right? Now, let's say I want to try something with this, meaning I make a guess. So let's say my guess for the rate, which is, remember, lambda in Poisson, is going to be, I don't know, let me guess 4, on average 4 events per unit, right? And we can look at the Poisson distribution over here, and hopefully if the thing loads, we'll get to see the equations as well. Stuck. Let's reload. Okay, hopefully it'll come in soon. We want to be able to kind of figure out if I assume these things arrive in a kind of rate of 4 per whatever, per minute, per hour, each sample being 1 unit, what likelihood is it that I'll see this data? So there's about 50 points here. Let's see if this is done. No, there's something weird about either my browser or about Wikipedia. Let's see which it is. So let's take that, put it there. Apparently it's my browser rather than Wikipedia. Yeah, well, we'll use that. As a matter of fact, let's just get rid of Safari altogether and just go here. Okay, so there's something weird about Safari these days, so I'm just going to use Chrome. Anyway, we have the rate, and this tells us that over here we have the PMF, the probability mass function, right? For any given distribution. For Poisson, it's lambda to the power k, whatever your k is, times e minus lambda divided by k factorial. So, for example, if I assume 4, I can calculate the likelihood of this this observation using that. So I can just say, I can put this thing here and copy that equation. I'll say my lambda was this 4 to the power k. K is my observation, which is 3, times exponential of minus 1 times my lambda, right? Divided by factorial of the number, right? So this gives me the probability of this point being, this probability of seeing 3 in a Poisson process that with a rate of 4 is about 20%, 0.19%. And you can write this equation by hand, and we can kind of calculate the other one as well. You can fix certain things. So for example, I want the second one to calculate based on the second observation, but I want the rate to get the rate from this point always. So these B2s, I can actually, there's a trick in Excel or Google Sheets where you just can put these little dollar signs in front of a cell and the result is the same, and then it will do a suggested autofill. So you find probabilities of all of these guys, right? So a bunch of probabilities. Obviously, for example, if you're expecting 4 things per minute, let's say, just seeing 1 is a lower probability than seeing exactly 4 or close to 4, like 2 or 3. But seeing 7 is also less likely. So we have all of this. One other trick, well, not a trick, but convenience is most kind of spreadsheet programs actually have these functions, these distribution functions inbuilt. So you can actually in Excel or in Google Sheets, you can just call that directly. So instead of writing all of this stuff over here, I can say take the 3 and take the 4. It expects 3 arguments. Okay, what's the it has the convenience that it asks me whether it wants me. I want the result cumulative or a point estimate. In this case, I want point estimate. Cumulative, like we saw in the class, it would give you the CDF, meaning not the probability of getting 3, but the probability of getting 3 or less. So for cumulative, I'll say 0. I don't want the cumulative. And you notice that it's all going to be the same. Again, I'll do this trick where I'll fix the rate at a certain point. Okay. And as you will see, the whole thing, you'll get identical results. So Poisson is already inbuilt. So whenever you can, you tend to prefer the inbuilt version, but that doesn't mean you can't write it by hand if you need to. So for example, if you have a distribution like, I don't know, the Dirichlet distribution or something like that we will see later on, it won't have a function in Excel or maybe even R. So you can just write it by hand and get the same result. For now, I'm just going to fix this so we use the actual thing. Poisson with the number and with, what was it? B2. Oh, and obviously we don't want it to be cumulative. So I'm doing this in a spreadsheet just so you see that what we're doing is nothing too complicated. You can even do it by hand. So I'll just spread this over the 50 numbers, and you basically get each one. And notice that what the little dollar signs do is it tells Excel or Google Sheets that when I drag this over to the others, update this first one, so that in the first one it's A7, A8, A9, etc. But basically the dollar sign means the other one is locked. Always take it from the same absolute position. So that's that. So I have the kind of the likelihood of each point. Now the question is, what is the likelihood of the whole data? And we saw that that's simple. I can just say the likelihood of the data is essentially, remember that likelihood is the probability of the data given the parameter. In this case, our parameter is the lambda. What is the likelihood of all of this data given this particular lambda, this particular 4? And it's easy to calculate. You can basically, it's meaning what is the probability of getting the first number times the probability of getting the second number, the third number. So what is the joint probability of getting this exact set? So you can say product of all of these probabilities from what is it, B7 to B56, apparently. B56. So this whole stuff, get the product of that. But mostly this won't happen in R, but in Excel or other, for example, on a calculator, what you'll get is 0, which doesn't make sense. Why this happens is these are very small numbers, all less than 1, obviously. If you keep multiplying them with each other, you're gonna get, it's gonna underflow, meaning it's gonna be below the precision of the actual kind of the program you're using. And you can see this easily. For example, if I take the first few, it's still 0. Let's try the first 8 or so. Now you get a very low number. And after that, maybe about after the 17th number, or actually the 10th number or so, it underflows. So that's no good. We want to see a number. And remember, we actually did that in kind of talked about that in class. Instead of using the probabilities themselves, it's a good idea to actually use the logarithms of the probabilities, right? So now I can just spread this downwards. Notice that I'll get a bunch of kind of negative numbers, since the logarithm of a number less than 1 is always going to be negative. The logarithm for 1 is going to be 0. And now, instead of a product, since the multiplication of several numbers is the same thing as taking their logarithms and adding them up, we can just sum these. And now it's not this much though. We want to sum the whole thing from here to the end, right? Which means I get I get, so B7 to B56, I get minus 108. You can always try and convert this into back into a normal number. Again, it will be 0. If you have a better calculator, maybe it might work. Let's try with my kind of desk calculator, so to speak. This has better precision. I'll take that, plug that in, and take the exponential of it. Oops, sorry. See, I think it's here somewhere. Yeah, e to the power 8. Yeah, it's 4.6 10 to the power minus 48. It's a minuscule number because the exact probability of having this exact outcome is very low. But now that we have the logarithms, we can actually kind of give a number to that very small probability. And now we can ask whether it's more probable under 4, or let's say, is it more probable under 3? Notice that the log likelihood increased. It's a number closer to 0 now, as opposed to 4, which was 108. Minus 108, meaning it's a lower number. With 3, obviously, now everything gets re-evaluated. It's minus 95. We can actually look at that in pCalc again, just to convince yourself that the power e of this is only minus 42. So it's, again, a very small number, but at least it's a higher probability, meaning this data set of 50 numbers is more probable with a rate of 3 if you assume 3 things happen every unit versus 4 things. What about 5 things? It gets less likely. So 4 is more likely than 4 is more likely than 5. 3 is more likely than 4. Let's look at 2. 2, notice that 2 is actually less likely than 3. So probably the likeliest one is somewhere between 3 and 4. 2 and 3. So the thing is, you can actually find that exactly. There's what we're trying to estimate is the mean, and generally for each kind of distribution, the most likely estimate of the mean is already given. So it is basically the mean. The most likely estimate of the mean is lambda. So if I calculate the mean of these numbers, it will give me a good estimate for lambda, the most likely estimate of lambda. And we can actually do that. Let's go here and say mean is equal to the average in Excel speak of all of these numbers. Ooh, too much. Till 56. And the mean is 1.9 something apparently. And if I give that, oh, I'm doing the wrong one, sorry. Mean of not B7 to B56, but C7 to C50, oh, not C, it's A. Yeah, let's see. Yeah, this is the data. So the mean of that is 2.52. So notice if I give it 2.52, I get the smallest one yet. And even if I give it T.52, T.53, I think it grew. Let me see, 2.52, 93.208. Let's try with 1. It's a more negative number. And same thing for that. Again, more negative. So actually, what you're getting with this estimate, this analytical estimate, by just taking the average, is the best estimate of lambda. So basically what this line tells you that the mean of the observations is the most likely estimate for lambda in the case of Poisson distribution. So this is how you would do this by hand. And we can kind of possibly, let's go to RStudio, try the same thing with R. Let's make a new R script. So what I'll do is first I'm gonna change my directory to where we are. So where are we right now? Where did our studio start? It started in my home directory. So I'll set that home directory instead under Dropbox, under courses, BIN504, oh, not 501, BIN504 terms, fall 2022 under code, and we have this little, yeah, EM MLE example is what I want. So now I'm there. So everything I load will be loaded from this directory, right? These things we have here. Good. So, well, first I'll do is I'll take my data, and let's say we're using the Poisson thing. So read CSV. Obviously, this file is not a CSV file. It's just a bunch of numbers under the same file, but it could have just as well been something like this, and the next one could be something like that. Then it would be a full CSV file, but this is still kind of a very minimal CSV file. It's basically a CSV file with a single column. So I can still use read CSV to read it. So I'll read Poisson data, and when I do read it, I get this weird data frame. I don't need a data frame for this example. It's just a vector of numbers. So there's one thing you can do. You can just say, I just want all rows and the first column, and rerun it. Now it's just a vector of ints. So if I just go here and look at data, it's just the numbers I had in the text editor over there. So now what I can do is, just like we did for did in Excel, we can use, so the first one was the log likelihood was minus 153. We can use the distribution function in Excel to calculate that. So, and in this case, it's the Poisson distribution, and we want the distribution function, which is the PMF. And I'll give it my data, and the lambda we chose before was 252. 2.52, not comma, .52, and it will give me a bunch of these things. Now these aren't we didn't take the log of these, but you could just say ln, in log, is there ln? No. Yeah, log computes the logarithm by, okay, so ln in R is just calling it log. If you don't give it a base, it calculates that. So this is it. Let's see how well they agree. Let's see what we did wrong here. Poisson, let me not take the logarithm for this for a minute. 0.21, and the Poisson of the data. Actually, there's something wrong here. I see. Notice this is a 3, this is a 0. So it didn't read the first data point, and the reason it did that is here. Normally when it reads from a CSV, it assumes that the first thing is the column name. So it does that, and now I should be able to get the same number. Yeah, 0.2145, 99. So the first number, and the second number is let's convert this back into ln. And now here we can also do an ln. And I'm going to show you something else though. So yeah, 153.89, 252, 159.57, and so on and so forth. So you get the same results, but you don't need, in R at least, you don't need to actually put this log here. R has the convenience in all of its distribution functions where you can actually say I want I want the logarithm of the result directly. So if you say true here, it gives you the Poisson distribution of the data. So again, I can just say take that and the sum of that, I get the result, right? So I can write a function here, just very simply, log likelihood Poisson, let's say LL Poisson is a function which sums the Poisson distribution probabilities of data, whatever data is. So this is going to be global, so be careful. When you change data, the outputs of this function will change. It gets this data from the outside. Normally you would want to do this like X data, but I'm keeping it simple today, so I'll just leave that here. So it will just grab the global data with some mean X, and I want log to be true. All right. So we'll define that function. Now I can give it anything. LL Poisson of 3 or 4 would be 108, like we found over here. Same thing, right? 108, 99, 108, 99. You can ask even for something like 40, which is very unlikely, and you get a very unlikely result. Actually, you can basically plot this, right? So we can say, let's create some candidate means, right, which will be a sequence of means from 0 to, let's say, 10, and the length out will be, let's say I want 50 of those, right? So now if I look at my candidate means, let's actually look at them here. Candidate means, they start from 0, going by 0.2 every time up to 10. So it's a uniformly spread out bunch of possible sample points on means. And then I can just say plot. Let's calculate the likelihoods. Likelihoods at the candidate means. For that, I can again apply apply to the data. Sorry, apply the data are the candidate means, and the function is LL Poisson. Apply is the same thing as apply. It's basically simple apply. If you don't have a data frame with several columns and several rows, just a single string of numbers, a vector of numbers, you can use apply because you don't have to specify margin. So let's find the likelihoods. Let's see if this actually worked. Likely, I called it likelihoods. Okay, so we get all of that, and yeah, we have our, for example, we should have our 108 somewhere there. 4 was 108, let's see, 106, 110, and so on and so forth. Obviously, we don't have exact 4. Yeah, we have 4.8 at 21, and that gave 110, which is close to 108, and 4.1 is close to 4, and the one before that is this one, 387, actually got 106. So yeah, this works. And now what we can do is plot the candidate means against the likelihoods, which I misspelled. And let's say the type of the plot is a line plot. Let's see what that looks like. Yeah, so you get this. And notice that probably the highest point here is at 2.52, which is what we expected. So the likelihood increases until you get to 2.52, and then other kind of guesses for the rate, the likelihood starts dropping. Perfect likelihood would have been at 0, but you will never actually see that in practice because It will only happen when things are not random. Okay, so this is maximum likelihood estimation. You can do it numerically like this, find the likelihood over a range of means and get the top one. Or you can pre-find the maximum like we did in class and like they did here, for example, finding that the lambda, the mean itself, is the best estimate, the most likely estimate for lambda. Is basically what they did is they put this PMF inside the mean equation like we did in class for linear models, and then just take the derivative, make it equal to 0, solve for lambda, and the answer comes out lambda. So that's what it is. So let's do this now this is for a very kind of simple thing. Let me actually plot likelihoods. Let's make this into a function as well, so that we can actually use it later on. We'll use the same candidate means for everything, so yeah, and these are all part of the same function. Let me change that, and this function will get as an input, we get candidate means are going to be generated statically. Likelihoods will be calculated with yeah, let me just give it the function I want. Likelihood, let's call it LL fun, and what it will do is it will use LL fun here. Now, so when I say plot likelihoods of the data with, let's say, ll.Poisson, just give the function name, I'm not calling the function, I'll get, did I get it? Let's remove this plot and try again just to make sure it works. Yeah, I get the same plot. So, and then we can try it with other things later on. So we've got two functions now. We have one that calculates the likelihood for the whole data set given the Poisson distribution and a certain mean, and otherwise we have the one that calculates, that plots that thing. And this will work in most cases, right? So let me just take this and duplicate it. Let's call this, rename Poisson, and let's call this, for example, rename to normal distribution. So now we have Poisson and we have normal. Now let's actually take a look at the normal distribution here. Gaussian distribution. We got Gauss's page, Gaussian distribution. There we go. So yeah, apparently it's titled normal distribution. Okay, so we all know that the actual function is this. It's a bit more complicated than Poisson. And you have, this is the PDF. Notice that in Poisson it was called the PMF, the probability mass function. Here it's called the probability density function. Because this is continuous, any given point doesn't have a finite it doesn't have a measurable amount of probability. For example, in Poisson, we could exactly give it 4, because the Poisson distribution, the random variable, either gives a 1, a 0, a 2, a 3, a 4, some integer number. However, in a real distribution, kind of a continuous distribution, there's an infinitely possible, uncountably infinite number of possibilities. They're real numbers, so any given point doesn't make sense in terms of probability mass. But the density is the same thing. It gives us an idea of how likely that region is, that region around the point estimate. So we can actually go and get a normal data. So now we have this stuff, and let's say we plug it in here. Obviously our calculations are all kind of let's say mean, mu, mean estimate, mu, it's actually mu hat, and for the Poisson, let's call it the rate estimate and lambda hat. Can I actually give these actual, let me see, lambda Unicode? It should be possible. Yeah, there we are. So do we have lambda hat? No. Okay, small Greek little lambda. I'll take that. So now this is lambda, and I wonder if you can do something like that. No. Well, just assume that lambda here is lambda hat, and this is lambda, and that's the mean. So we can actually put these a bit that side. Okay, and that's the likelihood. So that's for Poisson, and for now, for this one, I just want an estimate of the mean. Since you have lambda, you should also have mu. There we go. Can copy. Yeah. So this is our estimate for mu. Mean is the same, it's the average of all of these numbers. Likelihood will change. Actually, this sum will not change, but the way we calculate the likelihood of every single item will change. Again, you can go and hand code this. Now, one thing that's different here is this has two parameters. Remember, lambda Poisson just had lambda. This has mu and sigma, the mean and the standard deviation. But to keep it simple, then you'd have to guess two numbers, and it is possible. There's nothing kind of theoretically impossible about that. But for now, just to keep it simple, I'm just going to assume sigmas, the standard deviations, are 1. So these are bell curves that are kind of spread out by a standard deviation of 1. So I'll just say sigma is 1. And here I'll just calculate for the first point. Like I said, you can write this equation over here by hand, but again, there is a normal distribution function already available in Excel or whatever you want to call it, for Google Sheets. And let's see, what does it want? Yeah, it wants the x, and then it wants your mean, which was here. Mean is this guy. Oh. Because of the thing, I can't actually see the number. It's nice, isn't it? Yeah, B2. And again, we want to lock this so that all of the other cells use it. The mean estimate is B2. And likewise, again, what was the thing? Oh, it asks whether it's cumulative or not. We want no. Let's see what's wrong with this. Oh, it also wants the standard deviation, which we'll assume is 1. And again, that's going to be locked. So you get some probability. Let me make sure that I got this right, all the order and everything. Yeah, this is the actual sample. Mean is this one, standard deviation is fixed at 1, and the cumulative is 0. I don't want the cumulative, I want the point estimate. Okay, so I can just move all of these down, and I get a bunch of numbers. Okay, so yeah, so these are, again, they stay fixed, but I calculate for every one of these. Now, obviously, this is not going to be a sum. It's supposed to be a product. But again, if it is a product, you can guess that we will get 0 because it's a very small number. So instead, again, we'll do the same trick. Take the log likelihoods of each point, and instead take the sum. Okay. And now here I can actually take the sum of it, which will give me minus 144, and I can try different standard deviations. Let's say, what if it's 8? It's much less likely. What if it's 3? It's actually more likely. What if it is 2? More likely. What if the mean is 1? It goes back up, maybe 1.5, something like that. Again, if you look at the mean is mu. So the maximum likelihood estimate for the mean is mu, which means if I give it 2.37, I'll get the smallest, the highest likelihood. So this least non-negative log likelihood. Actually, this is not likelihood, it's log likelihood. I don't need that. Okay, so, and again, for the Poisson one, it's also log likelihood, which means it's ln of the probability of that. Okay. So that's the normal distribution. And again, we can try the same thing here in R. We had a log likelihood for Poisson. We can actually make that into a log likelihood of, let's say, normal. And the only thing that's going to change here is going to be, this is going to be d norm now for the normal distribution. The data stays the same. We need a mean, which is going to be x, and we need a standard deviation, which we assume to be 1, and log is again going to be true. So let's define that function. And let's say I read my data now from, what was it called? Norm data 1. Norm data 1. Okay. Read the data, and now I can just say plot likelihoods of that data with LL norm. And if I look at the values, oh yeah, we want to run that. We get this likelihood graph, which is not bad. Again, probably the best point is 2.5, which is the maximum likelihood estimate. And if I kind of look at another normal data, it would give me something else, right? So it turns out that here the normal is somewhere here. And actually, if I take the mean of the data, it's 6.9, and yeah, the highest likelihood is around 7, which is good. But all of this is just simple stuff, and you might be asking yourself, if I can just take the data and take the average of it, if I get the estimate, what do I care? But this is a more generalized method. It allows you to calculate the likelihood for everything. In this case, we're calculating the likelihood of the mean, obviously, but for example, let's look at something more complicated like the Dirichlet distribution. Okay. So the mean might be something more complicated, and it has other parameters. So for example, the mean here is not the actual is not a single parameter. It's calculated as a mixture of parameters. And for example, for the Dirichlet, the parameters are alpha 1 through alpha k. Usually k is up to 3. So it's the mixing ratios of, for example, compositional data. In that case, there is no kind of straightforward way of necessarily calculating the best estimates from alpha 1, alpha 2, alpha 3. You might need to use something like maximum likelihood estimation, but the PDF is still there. You plug in the alphas that you guessed and plug in the data and calculate this function at any given alpha level, and you'll get some likelihood. And then again, you can plot them over here to find the highest likelihood. That would be the best combination of, say, alphas for this distribution. So this is a general tool that allows us to do simple stuff like kind of calculate the best estimate for the mean of a simple distribution. And for that, it would be obviously overkill because you don't need kind of that much this much machinery to just take an average. But it just goes to show you that you can use this machinery to calculate or estimate the most likely value of any parameter of any distribution, because all you need is basically the PDF or the PMF of that distribution, and you plug it in with the data and make your guess, and you come up with a likelihood. After that, it's just optimization. You can just scan over all the likelihoods, get the best one. Scan over all the possible parameters, get the best likelihood. Sometimes it can be done analytically. Sometimes it can be, you can use a numerical optimizer. Sometimes it's a lot more difficult. Like we talked in class, in a neural network, you want to find the most likely values of 1 billion weights, and then you use something like a GPU to actually try a bunch of different weights and move towards the region of highest likelihood. But the idea is always the same. Now, that being said, let's actually take this and duplicate it again and rename this into a mixture of normals. So now I'm going to change the thing a bit. Notice that we had two normal distributions, two pieces of normal data. One was around 2.5, the other is most likely around 6.5 or 7 or something like that. Now what I'm going to do is I'm going to take this first data and create a new text file and plug that in, and then take, was this the first one? 172.07, yeah, and take the second data and just add it to the end, right? So now we have 100 points instead of 50 each. And what I'm going to do is I'm going to shuffle all these lines and shuffle it again and shuffle it again, just so it's nice and well mixed. You don't need to do this, but just so to convince ourselves that order doesn't matter. So we have a bunch of numbers, and some of them come from the first distribution, some of them come from the second distribution. And what I'm going to do is save this as norm mixed.txt and copy this and plug it into here. So now we have a bunch of other stuff, and now also we need to obviously grow this downwards to that. And also, where does this end? 106. So make this into 106. So we have a different likelihood. These stay the same. So basically it says that the new mean is 465, and this will still work. If I say 465.8, I'll get 271. And if I say, for example, 4, it will be a bit better. Oh, the mean is wrong, sorry. This is up to 106 as well. So yeah, 462, 463.7, I get 271. Otherwise, for example, if I just slightly move it, A7 to A106, yeah, something. Okay, so let's take that and plug that in. I get 271. So what if I pick 4? I get 265, which is better. What if I pick 5? It's a bit higher. What if I pick 1? It's much worse. But now something doesn't quite work right. And let's actually... oh, I'm playing with a sigma. Sorry. That's the problem. 363, 463, I get 395, and then sigma is supposed to be fixed at 1. It should never change. Because we assumed it was 1, and I know that it's 1 generating the data, so we're not going to play with that, but you could. So if it's something slightly different than that, I get a lower likelihood, or slightly different on the other side, let's say 4.4, I still get a lower likelihood than when I was using the estimated one, the most likely estimate, which is best. Okay, so what does this look like when we are actually doing the same thing with norm mixed? So I'm just going to copy all of this stuff over here and calculate norm mixed and run this. Yeah, it gives you 460 something, and just by looking at this data you might assume that, yeah, this is a normal distribution and it works just fine. The problem here is if you actually take a look at the distribution, the histogram of the data, if you can, some data you can't, but in this case we should be able to, because it's just a bunch of numbers, it's not multidimensional. Obviously it's kind of it's two peak data, right? So it's a mixture of two things, and it obviously makes sense that the mean is the center of gravity of the distribution, the center of mass. But funny enough, where it says that you have the best kind of the highest rate, the highest likelihood for the mean is actually where there's very few samples. So this happens very often when you essentially underfit your data. Your data is more complicated than your model, but the model does the best it can and tries to fit it. So now we have a problem. We need to find out which one actually kind of gives us, we have to find essentially a better model. And now we have to figure out whether kind of two Gaussians like this, a mixture of two distributions, fits this data better than just one distribution. So let's try it with two distributions. Now instead of the second one, will also have a sigma of 1. Let's say the first one has a mean of 2, the second one has a mean of, let's keep them extreme. Let's say this one has a mean of 0 and this one has a mean of 10, right? And we'll have two likelihoods in this case. The mean estimate is still the same for everyone. So now what I'm going to do is copy this over here and fix it. So we still want A7 as the input, but now for the mean we want this one. We want C2, cell C2. And we want C1, right? So this standard deviation and this mean, and then calculate it for this number, okay? All right. I'm just checking to see that everything's right. Okay, and suggested autofill, yeah, go ahead and autofill. So now we have different likelihoods for two possibilities. Now what I'm doing here is this. Let's copy this image just so I can show you. Let's open it up in an image editor. Now obviously here I am trying to draw with my trackpad, so actually, yeah, I have the mouse. I'm trying to draw with the mouse, so it's not going to be very clean, but let's say. So this was our initial guess, the blue one, right? We assumed that this was a single Gaussian, which would be somewhere around, the mean would be somewhere around, I don't know, maybe 4.6, 4 point something. And that gave us some likelihood and some best case mean, but obviously this is not a single Gaussian. So my idea is, what if this is made up of two Gaussians? Let's say the green Gaussian, which is somewhere here, and the red Gaussian, which is somewhere there, right? And if I add these two together, will I get a better explanation for this data? And that's what we're going to try. And now here, for example, initially for the green Gaussian, we said the mean is, let's say, 0. So actually this green Gaussian would have been somewhere here at 0. And the other one, we said that the mean is 10. So these are our guesses for the mean. So we said the mean is 10, right, over here. So this is what it is. Now we want to calculate the overall likelihood when you have this case. Now the problem here is there's about 100 points here, and we since we mixed them, we know about roughly 50 of them belong to this one, and the other 50 belong to that one, but which belongs to which, we don't know. Probably points that are closer to 0 belong to that one, numbers that are closer to 10 belong to that one. So let's say I have one, let me use, for example, purple. Yeah, so let's say I have a number like one observation around 2, right? So, and we do have observations like 2. We have 2.7, we have 2.5, maybe something closer to 2 here. Yeah, 1.68. Now, 1.68, is it more likely for this Gaussian or more likely for that Gaussian? So let's say this is the 0 probability and this is higher probabilities. When I look here, the probability that it's on this Gaussian is some probability, but if I notice that these things are infinite, so this actually goes down and down and down and down until infinity. Actually, it goes much faster into infinity. So here, for the red one, the probability is much smaller. So now, for this point, I can say, well, it belongs to the green one more than it belongs to the red one. And we don't need the blue one anymore, because the blue is, we decided we're just going to do a mixture of 2. So this point here, the 49th point, is probably more likely from the first distribution than the second distribution. And you can do two things here. You can actually decide, I'm just going to assign this point to the green one and it'll be part of green, or I'm just going to assign it to red. It's going to be part of red completely. Or what you can do is do a blend, right? You can say this point will belong to a distribution with a probability proportional to the likelihood of that point for each one, right? So let's say if this is a likelihood of 1, and that one, the purple one, is a likelihood of, let's say, 3. There's I can do a 3, let me see. It's difficult to draw with this thing. Okay, so 3, this is 3 and this is 1. Total likelihood over distributions here would be 4, and I'll say x is 1/4 part of the red distribution, 3/4 probability a part of the green distribution. Actually, not a probability, but that's mostly, let's call it a weight. So for each point now, we can actually calculate, and let's say insert one row above. Let's call this normal, let's say components. Let's call them components. This is component 1. This is component 2. Parameters. And this is the component 1 params. And again, for the whole data set, you can actually calculate the likelihood, right? So this is the sum of all the likelihoods of all the points for the second component. This is all the likelihoods of all the points for the first component. And the data overall, component 1 seems to be more likely than component 2 because it's a smaller number. But we're going to kind of mix them now. Now what we can do is essentially here, let's say C1 weight, let's say total weight of both components. What we can do is basically add these two together. Yeah, suggested autofill, thank you. The problem here is these are, remember, just these are logarithmic likelihoods. And when you add logarithmic likelihoods, we would be actually multiplying these, so we don't want that. So for this one, we'll just change them back into normal numbers. So it's going to be some number between 0 and 1, right? And we'll kind of do that. Okay. And now we have the total. So this is analogous to saying one was 1, the other one was 3, so the total is 4. And we're going to use that to normalize. So now we'll use component 1 weight, component 2 weight is going to be equal to, this will be exponential of, again, we're inverting the log, kind of actually reverting it, divided by total weight, divided by total weight. Yeah, suggested autofill. And the second one will be component 2's likelihood divided by the total likelihood. Actually, no, this is D8. And we need to kind of revert the log on this. Yeah. So now look at this. The first point is 1.84, and there's two distributions. One is at around 0, the other is around 10, which means if the point was at 1 point something, it's most likely a part of the first one rather than the second one, which tells us actually here, yeah, the weight for component 1, the green one in our figure, is 1, the weight for the other one is 0. And vice versa. For example, the other number was 7.4, the other observation, so it's somewhere here. So that's more likely with the red one rather than the green one. So we have weights for everybody. That's nice. So now what we can actually do is essentially use this information, right, to calculate, for now I'm just gonna let's get rid of log for now. I'm just gonna do that plus that, right, and fix this as well, because the arithmetic is going to work better in this case, and fix that as well. and these will not be logarithms. It's going to screw up our likelihood calculation, but let's see if this actually works better. So yeah, that's correct. These are all correct. Yeah. So I'm just going to take that and move it up. It shouldn't change the overall thing, and move it down. Now from here all the way down to the end of the data. Right. And the log likelihoods obviously don't make sense anywhere. These are supposed to be products. And product here. Okay, so, and these come up as 0, but we expect them to be 0 because the multiplication of all of these small numbers is essentially 0. And notice what happens here. 1 0 0 1, and this is basically 1, this is basically 0. Somewhere around the middle, for example, this is about 2% to 98%, part of one or the other. Something right in the middle, something like 6 4. Trying to look for a better membership, kind of a mixed membership somewhere here. Let's see. No, this is actually good because the data is more or less separated. The values in the kind of these all belong to this one, and those all belong to that one. There's really not much that's right in the middle. It seems more or less polarized, right? And between 0 and 10, the midpoint would have been 5. So the best case is we can actually try with one of them. Let's say this was exactly 5. And notice that it would be 0.5 to 0.5. But if it's even slightly closer to one of them, this one, for example, now it goes to the red, or it goes 5.5, it's completely in the red, right? So let's fix this. Okay, so if we find something that's very close to 5, I can't seem to find it in the actual data, but it should be here somewhere. This is not bad. Some higher 4 or lower 5 is what I'm looking at. Our luck, we don't have it. But yeah, that's the breakpoint at this point. So 4.23, no. Anyway, so we got the two weights. So now we know that each one belongs to, kind of each point has a slight belonging to one of these. Now, this is where EM comes in. So what we did here is we actually calculated the likelihood of each thing, and then we found the weights, right? So this is what's called the expectation step. I'm kind of finding the expectation of each point, right? So this point is kind of the expectation here is that it belongs to the C2 component, and so on and so forth. Now, given that these are the ones that belong to each, let me actually recalculate the parameters, which is the M phase. So let's call it this the E phase up to here. Actually, let me give it another row. So here we have the E phase, and now I'm going to do the M phase. So maximize the parameters, find the maximum likely parameters for each one, right? So again, the sigmas are going to be 1 and 1, just so you can follow. These are the new estimates, right? The mean estimate, normally here we just kind of we made initial guesses. These were initial guesses. Now that we have memberships, our second estimates are going to be based on the data. So now what we want to do is, this mean we calculated by kind of taking the average of all of the data. So A9 to A108. This one, for again, this is component 1 parameters. This is component 2. Sigmas we know to be 1. We'll just hand wave those away. Now we want to estimate the new mu for parameters after our expectation phase. We don't take the kind of all of the take the mean of all of the data points, because now we know who might belong to component 1. So for example, 1.84, if it belongs to component 1, it goes into the mean. Otherwise, if it belongs to, for example, the second point, 7.48, probably has no expectation on kind of component 1. So there's no point in putting it into the parameter estimation of 1 because it doesn't belong to 1. So the way we're going to do that is through a weighted mean. So essentially kind of like the way you calculate your grades. If you got AA on a course, you get full credits, so the credits times the quality. Otherwise it might be a larger kind of course, more credits, but if you didn't get too much on that, it doesn't add to your GPA. So same thing, it's a weighted average. The data times its weight plus the second piece of data times its weight plus the third piece of data times its weight, and so on and so forth. So the thing here though is, obviously you can, in a programming language, you can do this with a for loop. Here in Excel, they actually have a nice function. I think it's weighted average called, obviously it has to be a formula. Yeah, average weighted. So we'll have that, and the values are still the same. A9 to A109, so our data. Oh, 108, sorry. A9 to A108, but now the weights for component 1 are going to be E9 to E108, right? So weights for component 1. And that's our weighted average. So now it's 2.37. Notice that we started from an initial guess of 0. Now the guess is 2.37. We don't need this. And for the second one, likewise, I can actually probably just, let's make this again locked on the data because that's not supposed to move. But the other one can move to the next one, and that's 6.9. Yeah, again, this data, but now with these dates, weights for component 2. So now I got new estimates for the thing, right? So this is the M phase. Now that I do that, so I calculated the new M. Actually, the E phase is calculating the new likelihoods and the weights. And the good thing with Excel is I can probably just take all of this. Let's now calculate for this new mean. So that, I'll take that. And here I want this obviously to be A9. I want to use this data point over here. And let's make sure we fix just the column. So when I copy this down, this will update to 10, 11, 12, but the A will stay the same. And this one is not going to be fixed anymore. It's going to be, for this one, I want this mean. And, and for that one, I want this sigma. Okay, so use the new mean and the new sigma to calculate the likelihood of the first point over here. And yeah, we're going to have to fix the row here so that it always takes the same one. Right. So does this work? Yeah, use this sigma and this mean to calculate the probability of that point. Yeah. So we can just move this all down and calculate the points for everything. Right. So these are the likelihoods for now our second phase. Actually, let me just, if I can, so now where are the little things for the lines and everything? I don't know. Borders, yeah, that's what I want. Borders, yeah, this is. So after this line is basically our second iteration, right? The first iteration, there is no M phase, we just guessed the parameters, and then we did the E phase, and now in the second M phase we calculate the maximum estimates from the previous E phase and now the new likelihoods. And we're going to do this for the second component as well, which is going to use again A9, and it will use H4 and H3. Very good, so this is fine. I'll just copy all of that down. So now we get a new set of values, right? A new set of likelihoods based on these estimates. And we can actually calculate the weights as well. The weights will be calculated. The totals are the same. So I can just copy this over here. Yeah, this is the total of these two. And these are all the total of that divided by the total. And this one is that divided by the total. So again, C1 weight and C2 weight, and this is for iteration 2. And I can take all of these and just copy them down, right? And now notice that this was 1 to 0, very sharp. Now it's not that sure anymore because this has moved to the center. And what happened here was, if I go back into our thing, this was originally at 0. Now the new estimate has it somewhere around 2. And this was originally at 10. And now it's somewhere around 7, right? If I'm not mistaken, yeah, this is going to be somewhere here at 7. And this one, we don't need that anymore. And this one will be somewhere around, what was it? 2.37, yeah, somewhere there. So now they move together. And notice that they moved where they're supposed to be now. And therefore the membership kind of changed. So 2 to 7, that's about 4.5. So something around 4.5, some sample around 4.5 should have mixed membership. Let's see if there's something like 4.5 here. There's 4.4, and notice that it belongs 70% to the first component, about 30% to the second component. Now you have, and that would be a point somewhere around here, right? So it probably is here, so it belongs more to this one than to this one, but it's close. And the rest in EM is just the same. You keep doing the same thing over and over again. Now we need a new M phase. I'll just copy all of this, right, into here, right? And notice that since it's Excel, everything just works. It takes the same data, but now these weights and the other one as well. So notice that the mean slightly changed. And again, let's put a nice border on the side. So this was the first beginning, first iteration, second iteration. Now we're in the third iteration of EM, and we can just copy all of this stuff, hopefully, and it should just work. To that. Let's make sure everything works. This one uses A9, so yeah, the first item in the first data point with L4. Where's L4? Yeah, it uses the correct mean, correct standard deviation. This one uses the correct mean, correct standard deviation. And the numbers changed a bit, but not too much. So 2.37 to 2.34, 690 to 6.8. And basically the rest of EM is just doing the same thing all over again, right? So I can copy this and do one more iteration over here. 3.33, 84, very small change. Do it again. Much smaller change. Let's, can I do it again? Huh. I don't know why. Apparently Google Sheets goes only to Z, so I can't do the next one. But what I can do is take these guesses, right? Copy. Let's make sure we copy the values. Yeah. And I'll use those as my initial guess. Ooh. Yeah, we'll just plug them in by hand. 2.33, 39075. That doesn't matter, just 3.1. And this one would be 8.84, 14. Let's call it 15. No, that's not 68, it's 6.8. Notice that it's 3.339, 3.355, or it's basically stopped. It stops changing after a while, right? So this is almost exactly that, and that's almost exactly that. So after a point, you can set this to be a threshold. So if you say, for example, if the means don't change after the fourth digit, which would make sense here because we have basically 4-digit significance after number, 2.3334, 2.33334. If that doesn't change after that point, it's done. I don't have to go any further, and you can just stop there. And that would be your estimate for the first component and the second component. And you can actually calculate the weights. So you can say sum of all of the weights for that, yeah, and sum of all of the weights for the other one, 48 to 51, which is exactly what we expect, right? So this would be, we call it Z. How many of the points belong to one distribution versus the other? And they were 50-50, so this is a good estimate. So you can do the same thing here probably. Again, 50-50 about. 50-50 here. Slightly different, but still 50-50. Slightly different, but still 50-50. But notice that in our initial guess, 1 to 10, yeah, there were still 50, but notice that this had more in the initial guess, then it reverted to the other way, and then it essentially normalizes. If I had made the first thing very far away, like I don't know, 20, notice that most of the weight will be on the first distribution because this red one would have gone off field, right? So initial guesses are important. So let's make this like 1 to 9 so that it does converge till Z. Yeah, well, 33, 36. Anyway, so this is where you come to. But if, for example, if you give it a very bad initial estimate, let's say the mean estimate of the first one was -5, and the mean estimate of the second one was -10, right? Notice that this is equivalent to saying my original, the first distribution is over here, and the second distribution is all the way back there. Now it has nothing to do with the data. It's kind of, sometimes you can't see the data, so this might happen by accident. But if this is the case, then it's not going to converge to a nice place, because they will kind of all try to handle this part, probably leaving the other part empty. So EM is kind of dependent on the initial guesses, and we can actually try that. Notice that it actually converges. Yeah, it actually did work. Notice that the order is different, but it's close enough, 6.8 to 2.5. And as a matter of fact, this data I did create it with 2.5 to 2.5 to I think 7 or something like that. Let's try that. 2.5 one mean, and the 7 would be the other mean. Yeah, it does converge quite quickly, and this is what it finds. Right. So this is basically EM, right? And this is all that the code that we do in kind of in class. This is all that it calculates. The E step calculates the new likelihoods, and then the weights, and based on that, the M phase calculates the new parameters. The next E phase uses that to calculate the new M's, and so on and so forth. So before I end for today, we're almost at 1.5 hours. What I want to do is go back to our original thing. I think it was called, what, EM demo? This was it? Yeah. Actually, let me... So, we don't need all of these slopes and intercepts and etc. Initial parameters. Let's use the initial parameters. So, for example, for where are my initial parameters? Yeah, there we are. Let's take this, and I'm just going to use a normal script here, R script. Yeah. So in our case, for this Gaussian example, we just have two initial parameters, right? Mu of 1 and mu of 2. That's all we need, because otherwise, I mean, kind of, we know that the sigmas are 1. So what I'm gonna do is just gonna say M1 and M2, the mean of component 1 and component 2, and that will be M1 and M2. So this is what we did in the beginning. It will just give you a kind of a random point in the graph, in the space, and I want that random point to be between 0 and not 2, because 2 is a bit small here. Let's say between 0 and 10. Right? So if I run this, the first one is assigned to 1, the second one is assigned to 9.5, just like we did over here, right? We give the first one to 0, the second one to 10. This works similarly, right? Those are my initial parameters. So let's go here and let's look at my E step. I don't need the plot. There we are, the E step. Yep. E step for my case should work just fine, right? E step, except I just have 2 weights. I have 2 components, not just kind of in our example in class. Remember, we had essentially 3 lines, so it was 3 weights. Here there's two Gaussians that we want to fit to this thing, so it's just 2 weights. Likewise, in your homework, there's 2 kinds of flies, right? So 2 components. So for each row in the data, that's good. Calculate the deviations. we don't have deviations because these aren't lines and points away from lines. We just have likelihoods directly, right? Because these are directly sampled from the Gaussians. So we don't have that. We just need the the pi's, right? The p over here. And our data is just going to be a single row, right, of numbers. So n row and data, so I don't need actually the number of rows. Let me just hard code this. I know that there's exactly 100 points here, so I don't keep this simple from 1 to 100. So these likelihoods, remember, we calculated based on these are these likelihoods, right? Normal distribution for that point given my guess of guess of the mean plus standard deviation of 1 always and non-cumulative. So I can do the same thing here. I can say d norm, right, of data I, the ith data. My mean is going to be params 1, because that's the first component, the mean of the first component. And standard deviation is always 1. And yeah, I want the, do I want the log version? No, I don't want the log version. So this should work. Yeah, x is data, mean is params 1, st is 1. Actually, I don't need to give the st because apparently the default is the data, it's x, mean is whatever you give it, and st, if you don't give it, it takes it as 1, and log takes it as false, so that's what I want. And now for the second one, data I, this time I want the second parameter because I want to calculate those. Total weight would be P1 plus P2. So this is what we did over here. Just add these two. And therefore what we want is, yeah, renormalize the probabilities. Again, actually, let's keep the comment. Comment didn't hurt anybody. W1I is P1. Oh, we already calculated that. We don't need to calculate it again. P2 divided by total weight, and give me back W1 and W2. So this is the E step, right? So it brings us over here, which is where we put the line. So the first E phase is done, and then we'll use that for the second M phase. Now the second M phase, we'll just steal our code from this thing over here. Where was my M phase code? From before, M step. Actually, in this case, the M step for the lines is much more complicated than what we need. M step takes the data and the W's, so these are the W's we just created. A bunch of stuff here I don't need. I don't need to solve a linear equation because we don't have lines here. I just want the parameter 1 and parameter 2, right? So all this has to give me back is parameter 1 and parameter 2, which we called kind of M1 and M2. So M1 and M2. And notice that, well, how did we do it in Excel? We said, well, M2 is basically the weighted mean of all the data given the memberships, which is for the first one is the weights given from the old one. So M1 is basically mean of the data with, how do we do weighted mean here? Okay, let's ask help. I thought mean had weights here. Weights. Weighted mean. Stats weighted mean. Oh, it's called weighted mean. That's convenient. Weighted mean of the data, and yeah, that's x is the data, and then the means numerical vector of weights, same length as the data, giving the weights to use for elements of x. Yeah, that's exactly what we want. And the first one is for component 1. These are the weights we get from the outside. So weights get me the first one. And the second one is likewise the same. 2. And this is going to be 2. And that's our M step, right? So let's evaluate all of this. Source, run all of that. Now we can actually use it with our data. Do we still have our data? Data is 100 things, yeah. So we'll start with the first E step of the data, which we have. Parameters are our params, and sigma. What is sigma? Oh, we don't use sigma. That's from the previous one. Sigma was when to stop. We'll do that by hand. So let's run that again just to make it sure. So E step of the first run of E step, denorm object param not found. Denorm params, okay. Data params 1. Oh, it's supposed to be params, sorry. Yeah, so we get the weights for the first group, and notice that with params, our parameters were 9.61, 151, whatever. If I actually go back and plug that into this and take the second guess and plug that into that, C1 weight is 00083 whatever, and here it's again 00083 whatever. So this is doing exactly what we did in Excel. So just because it's R, you shouldn't assume that it's doing something magical. This is basically what we did by hand, happening programmatically. So we have our E step and M step. So now I can take those params, and params is M step, and this was my W's, my weights from the E step. And what does M need? Again, it needs data. What else does it need? It needs W's I just created. And then let's take a look at params. So if we run this again, W's should have the same length, don't they? Let's take a look at W's. It's 100. Oh, this is a matrix, so this is W1, W2. So what I want is all rows first column, all rows second column. Run. And now if I run this once, the new guesses are 769, 96, 448. Run it again, again, and it's fixed, right? 684, 333, which is what we found using Excel from before, right? When we said somewhere around 0 and 10, at the end you get to about the same thing, which was how I created the data to begin with. And basically what we do here in the demo is forget about all the plotting, but what I just did here, rerunning the same thing over and over, this is what that for loop does here. Creates the new params, assigns the creates the new weights, assigns the weights to new step, gets the new params. So this part is identical to that part, except it kind of draws the same thing again and again just so you see it, but you don't need to actually draw it. So for your homework as well, you can actually go back to this code here. All you need to do is, instead of denorm, you need the likelihood for the exponential, and obviously that's going to work just fine. And then for the mean, here we're calculating the mean of basically we're doing a weighted mean because the best estimate for the normal distribution is the mean. So Gaussian distribution, if we look at here, there's something about Wikipedia. Yeah, the mean is the best estimation of mu, but for the exponential it might be something else. So you'll just have to go there to exponential, or look at the slides from the course and find the PDF and essentially kind of find the lambda based on that. But other than that, it's going to be nothing different than what we've done so far. Okay, so it's almost an hour, 40 minutes. It's a bit long, but I hope it helps you guys going forward with the homework and with EM. We'll actually do a more kind of complicated form of EM this Wednesday, but with mixtures of multi-dimensional Gaussians, which are less easy to do a simple example like this on, but much more useful in real life. So I'll see you guys then.